Swayam Prabha. Digital India. Educated India.
Welcome to lecture 14. We have been talking about performance characteristics of instruments and data analysis part 2. So, today's topic is statistical analysis of experimental data, under which we will mainly focus on probability distribution functions, and we will mainly talk about normal distribution functions or Gaussian distribution functions. Any measurement is associated with several factors which cause random error. The instrument readings exhibit a dispersion or scatter of data. This is because the measurement is associated with several factors which cause random error. So, the measurement readings will always exhibit a dispersion or scatter of data. If a measurement is taken for a very large number of times, a probability distribution can be obtained from the data, and that is what we will learn in this lecture. Let us consider this table. This table shows 60 temperature measurements of some hot object. The readings are arranged in order of temperature. So, it varies from 1089 to 1115 degrees Celsius. On the left, this is number of readings. What it means is 1089 temperature 1089 degrees Celsius was obtained once, 1094 was obtained twice, 1104 was obtained 12 times, 1108 was obtained 5 times, so on and so forth. So, on the left, this number of readings essentially indicates the frequency of distribution or the frequency of the occurrence. Now, given this data, we can find out the basic statistical parameters such as mean. The definition we have learnt in the previous lecture. Median can be obtained as 1104 degrees Celsius. Mode is also 1104 degrees Celsius. If you remember, mode is the observation that occur most frequently, and this is what happens here. 1104 has happened 12 times. So, mode is 1104 degrees Celsius. Standard deviation can be computed using this formula, where xi is the individual observation, x bar is mean, which is this, and capital N is the number of observations. This standard deviation happens to be 5.79 degree Celsius. Variance is square of standard deviation, and that is obtained as 33.49 degrees Celsius. Look at the formula of standard deviation. We divide this quantity by n minus 1. For a very large number of readings, perhaps it will not matter whether you divide it by n or n minus 1, but smaller size samples will always divide it by n minus 1. Accordingly, they are known as biased or unbiased estimates. So, we can calculate these statistical parameters easily. Now, we can also have an histogram plot. So, by histogram plot, what we first ask is, if I divide this temperature range into small beans of say 0.5 degree Celsius each, how many readings will fall in each bean? So, from 1085 to 1090, I have considered one bean, 1090 to 1095, I have considered another bean, so on and so forth. Then from here and here, I count how many readings are there in each bean. So, this is that number of measurements or readings. So, basically this is the frequency of occurrence. So, this plot, this is known as a histogram plot. So, it pictorially presents the distribution of the data. Now, let us define a term Z, which is as follows. I find out number of readings in each bean or interval, whatever you call it, divide that by total number of readings and divide that by width of each bean or interval. So, with this definition of Z, I now plot Z versus those temperature readings. Now, the area of each bar is equal to the probability that a specific reading will fall in the associated interval. So, the area of this bar is the numerical value of the probability that a specific reading will fall in this interval. So, it naturally follows that the area of the entire histogram must be 1, because a reading will have probability 1 to fall anywhere within the histogram. If we have a very large number of readings and thus can make the bean width very small, the steps in the graph would become smaller and smaller and the graph would approach a smooth continuous curve. What I mean is, if I really have very large number of readings, then I can have very small intervals or very small size beans, and even then I can expect that the beans will have some finite number of readings in it. Under this situation, the steps in the graph would become smaller and smaller, and the graph would approach a smooth continuous curve in the limit of very large number of readings. The function z equal to f x is then called the probability density function. Here x is the value of the temperature, which is being considered as a random variable here. So, what I mean is, if I now consider these beans very small, then perhaps you can have a continuous distribution like this. But before that, you have these very small beans throughout. And if you really have very large number of data, we can do that. If you have really very large number of data, we can do this and still expect that each bean will have some finite number of readings in it. So, the function z equal to f x under such situation will be called the probability density function. So, the probability of a reading lying between A and B is given by the area under the curve between these two points. So, this is z equal to f x relation. You can consider it was initially an histogram, and then I made the bin size is extremely small, so that I was able to draw this smooth continuous curve. So, what is the probability that a reading will lie between point A and B? That means, what is the probability that x will lie between A and B? That can be obtained by finding out the area under the probability density function curve between points A and B. So, the area under the curve can be computed by this integral. So, the probability that x will lie between A and B is equal to integral a to b f x dx. You know that this term represents the area under the curve f x. Here f x is z. The probability information can also be given by cumulative distribution. Probability that a reading is less than any chosen value of x represents cumulative distribution. So, the cumulative distribution is defined by this integral. So, it is the probability that a reading is less than any chosen value of x. So, this is the cumulative distribution. Consider the point x 0, consider the value of the observation as x 0. So, what is the probability that a reading is less than x 0? For that, we find the area under the curve to the left of a vertical line drawn through point x 0. So, this area. There are several probability distribution functions, and among these Gaussian distributions is very popular. for performing statistical analysis on experimental data. The Gaussian distribution is also known as normal distribution. Most random errors follow Gaussian distribution. So, what is Gaussian distribution? Let us look at the expression that describes Gaussian distribution. A Gaussian distribution is characterized by two terms. One is mean of the distribution, another is standard deviation of the distribution. And the Gaussian distribution is defined by this expression. P of x equal to 1 by sigma square root 2 pi e to the power minus x minus mu whole square by 2 sigma square, where mu represents mean of the distribution and sigma represents standard deviation. So, the Gaussian distribution or normal distribution looks like a bell shaped curve. There are two distributions shown in this figure, both has same mean mu, but different standard deviations. This one has standard deviation sigma 1 and this one has standard deviation sigma 2. Standard deviation sigma 1 is greater than sigma 2 in this figure. Standard deviation represents the spread of the distribution or scatter of the data. So, this one is a distribution where the scatter of data is less than this distribution. Gaussian distribution has several interesting properties. This represents Gaussian distribution and this represents the mean of the distribution. It is known that if you consider an interval which is plus minus 1 standard deviation around mean, then 62.26% of the observations will fall within this interval. So, what I mean is you have this mean of the distribution, you consider mu plus sigma and mu minus sigma. The Gaussian distribution is symmetric around the mean. So, in mu plus sigma, in this interval 34.1% of all the observations will lie. Similarly, in mu minus sigma another 34.1% will lie. So, within mu plus minus sigma 68.2 or 68.26 will lie. So, we call this plus minus 1 sigma as confidence interval and the corresponding confidence level is 62.26%. Now, if we go to 2 sigma plus minus 2 sigma around the mean, that means if I increase now the length of the interval by, if I increase the length of the interval to 2 sigma around the mean, it will be mu plus 2 sigma, mu minus 2 sigma. Within this interval 95.44% of the observations will lie. Similarly, 99.74% observations will lie within plus minus 3 standard deviation of the mean. So, these confidence intervals or these confidence levels can be computed for the normal distribution function. Remember these numbers. This is very interesting property of normal distribution. Few more words about confidence interval. We used to make an estimate of the population mean which takes the form mu equal to x bar plus minus delta. So, mean equal to x bar plus minus delta. So, mu lies between x bar minus delta to x bar plus delta, where delta is an uncertainty and x bar is the sample mean. The interval from x bar minus delta to x bar plus delta is called the confidence interval on the mean. However, the confidence interval depends on a concept called the confidence level, sometimes called the degree of confidence. The confidence level is the probability that the population mean will fall within the specified interval. So, confidence level is the probability that the population mean will fall within the specified interval. The confidence level is normally expressed in terms of a variable alpha called as level of significance, and confidence level is 1 minus alpha. So, 1 minus level of significance. So, alpha is then probability that the mean will fall outside the confidence interval. So, if this area is alpha by 2 and this area is also alpha by 2, so alpha by 2 plus alpha by 2 is alpha. So, alpha is the probability that the mean will fall outside the confidence interval. So, the confidence level is 1 minus alpha. How do I know that a given probability distribution is Gaussian or normal in nature? You have done a series of experiments. Suppose you have measured a standard known temperature several times, or you are measuring a random variable several times. Now, you have generated a set of data. Now, how do you know that this data will follow a normal or Gaussian distribution? There are two quick tests for this. One is a simple test. The simplest way to test for Gaussian distribution of data is to plot a histogram and look for a bell shaped form. So, these are the readings and these are the occurrence, frequency of occurrence. So, if the histogram looks like bell shape, you know that the distribution is Gaussian. Another is making use of normal probability plot. A normal probability plot involves dividing the data values into a number of ranges and plotting the cumulative probability of some data frequencies against the data values on special graph paper. So, there is a special graph paper available and you have a normal probability plot there. The line should be a straight line if the data distribution is Gaussian. Let us ask a simple question. Suppose that a standard or known temperature is measured 30 times with the same instrument and the calculated standard deviation is 0.43. If the instrument is then used to measure an unknown temperature and the reading is 110.4 degrees Celsius, how should the temperature value be expressed? So, the question we ask is, we know a standard temperature, known standard temperature, we measure it 30 times and calculate the standard deviation as 0.43. If the instrument is then used to measure an unknown temperature and the reading is 110.4 degrees Celsius, how should the temperature value be expressed? That means, I have to express the temperature as 110.4 degrees Celsius plus minus the uncertainty associated with the reading. So, in the previous lecture we have talked about standard error, which is standard deviation divided by square root of number of observation. So, let us first calculate the standard error of the mean. So, standard error of the mean can be calculated as standard deviation divided by square root of observation, number of observations 30 here. So, I calculate the standard error as 0.08. Let us now calculate the error within 95% confidence limits. That is, we calculate the value of the deviation d such that 95% of the area under the probability curve lies within limits of plus minus d. So, this is something which we must understand. So, we wish to calculate the error within 95% confidence limits. So, you have to first associate a confidence limits. So, let us say that we want to calculate the error within 95% confidence limits. What it means is that we want to calculate the value of the deviation d such that 95% of the area under the probability curve will lie within limits of plus minus d. It is like 1 sigma, within plus minus 1 sigma you have 68.2% readings will lie. Similarly, within plus minus 2 sigma 95.44% of all the readings will lie. So, you ask the question, within plus minus what sigma, say x. So, within plus minus x sigma 95% of the readings will lie. So, what is the value of x? If it is 2 sigma is 95.44, we intuitively feel that x will be very close to 2. Actually, it is 1.96. So, within plus minus 1.96 sigma 95% of the observations will lie. So, you get the value as 1.96 into sigma. So, the maximum error, the maximum likely error in a single measurement can be now expressed as error equal to plus minus 1.96 sigma plus the standard error, which is standard deviation by square root of n. So, you compute this sigma value, you put as 0.43, this standard error was obtained as 0.08. So, error is plus minus 0.92. So, the unknown temperature can now be expressed as 110.4 plus minus 0.9 degree Celsius. Let us learn about a theorem known as central limit theorem. Given the random variable x has a distribution which may or may not be normal with mean mu and standard deviation sigma. Samples all of the same size n are randomly selected from the population of x values. then the distribution of sample x will, as the sample size increases, approach a normal distribution. The mean of the sample means will be the population mean mu. The standard deviation of the sample means will approach sigma by square root of n. So, what it says is, if you have a random variable x which has a distribution with mean mu and standard deviation sigma, and samples all of the same size n are randomly selected from the population of x values, then the distribution of sample x will approach a normal distribution as the sample size increases. The mean of the sample means will be the population mean mu, the standard deviation of the sample means will approach standard deviation divided by square root of n, which is n equal to number of observations. There are other probability distributions, symmetric distributions, where mean equal to median equal to mode. You have a single mode here, you have two modes here, this is also symmetric. So, you have one mode here, you have another mode here, and mean and median is this. This is uniform distribution. These are non-symmetric or asymmetric distributions. This is negatively skewed, this is positively skewed. Note that in case of non-symmetric or skewed distributions, mean, median, mode are all different. Many statistical tests assume values are normally distributed, but be careful, this is not always the case. Always examine data prior to processing. So, when you are measuring a particular quantity and you have a set of data, and then you see that one or two data do not follow the trend of the remaining data. So, you ask yourself what was wrong in performing experiments. So, is there an way to eliminate such bad data? Chauvinet's criterion serves this purpose. It helps you to eliminate the bad data which are outliers. Chauvinet's criterion is used for eliminating dubious data points from the bulk of the data. Ratio of absolute value of deviation from mean to standard deviation is calculated and compared to Chauvinet's criterion rejection table, and dubious points are eliminated. So, what you have to do is, once you have the set of observation or set of data, you find out the absolute value of deviation from mean and divide that by the standard deviation for each reading, and then compare it to the Chauvinet's criterion rejection table which is available, and then the dubious points can be eliminated by comparing these two data. New mean and standard deviations can be computed after you eliminate the outliers or dubious data points. So, this is an example of Chauvinet's rejection table. So, this is ratio of maximum acceptable deviation to standard deviation, and these are the number of readings. So, if you find that for a particular case your number is more than this, that ratio of the ratio that we just learned in the previous slide, that absolute deviation from the mean divided by the standard deviation, so is more than this for observation, you can consider that to be a bad data and may be eliminated. So, we stop lecture 14 here.